Okay. Hi everyone, I'm Shiwei Liu. I'm a new PI at the Alice Institute and group leader at MPIS. And yeah, let me briefly introduce myself for people who don't know me. So I did my undergraduate and master in China, and after that I moved to Netherlands to do my PhD in Eindhoven. Then I spent 1 year at UT Austin, US, and come back to Oxford for another postdoc. And yes, finally I came here to join this great cohort. And yeah, that's it. That's my background. And my research interest, I put it this very ego way. So my overarching research goal is to advance the frontier of AI from multiple perspectives. Like I would like to enhance the capacity of large foundation models, make it more reasoning better or faster. Also, another main direction of my research is improving the efficiency of also the accessibility of AI, make everyone use it with fewer cost. Also, I would like to deepen the fundamental understanding of AI behavior. I also learned a lot from Maxim yesterday. It's so sad that you will move forward from this direction, but I expect I will bring more interest to you in the future. Also, I would like to explore novel architecture design to improve the capacity or efficiency. Also, I work a little bit on data curation. So basically except for safety, every direction of AI. And this talk, I will talk a little bit about techniques things, the curse of depth in large language models, which can cover what I have done in the past, and also what I'm working on recently. And yeah, for the path of my research, I work a lot on efficient LLMs, like how to make or machine learning, deep learning, how to make training inference development more efficient. And the technique I use covers sparsification or pruning, you can see, also quantization, low rank approximation. And after working on for several years, my one trick pony here is we can always compress more for the layers or components that are less effective. By less effective, it maybe is contribute less for the prediction or performance. Either there's many metric how to measure the importance of layers or components, either recently outliers for LLMs, or you can use some more fundamental method like random theory metric. Habitual self-regulation. I like this paper a lot. It's written by Michael Mahoney, and it just works. And no matter what metric you use, you always will find this trend. This is a layer-wise importance score across different models, and the higher means more important. And you can always see this trend. The deeper layers always place smaller rows, and this also reflect on the performance. If you prune, this is a layer pruning performance. If you prune every single layer, then you measure the performance. You can see deeper layers barely drop accuracy if you remove them. I'm not saying it doesn't drop any at all. It's just contribute less. And using these tricks, you can always do compression more aggressive, and it has a lot of applications. NVIDIA is fascinating about this. They just use pre-train a large model, then perform layer pruning, and fine-tune with a massive amount of resource data sets. You can have a small model without even with better performance. However, on the other hand, if it's your large language models can be compressed so much, on the other hand, it means you're kind of wasting your training resources, which can be 10 million, $100 million. That's a lot of wasting resource. And it just makes me awake at night to think about this problem. And then I trying to figure out why this is happening. So my 2 cents here. So I call it curse of depth in LLMs. It's not only for LLMs, it's also for, it's a long-standing problem. For ResNet, I think it's also existing. So the curse of depth saying deep layers in LMs contribute significantly less, but not nothing to learning and the representation compared to early layers. And my thoughts would be, ideally, I would like to all layers in one model should be well-trained, has diverse enough features that can maximize utility of your model. And to solve this problem, we have to figure out what is the root cause. Maybe I can ask a question here. Why do you think this? Why do you think that we always suffer from this? What's the root cause here? Is about architecture or data sets or optimizer? Go ahead.
I think the architecture is maybe not optimal. I don't know.
Yeah, perhaps. Yeah. This is what I thought actually, and I attribute this to the use of LayerNorm. So before this modern LMs like Transformer, BERT, T5, they use post norm. Now everything, I think, except for several Gemma, they use sandwich norm. All these modern LMs use pre-norm. And what's difference here? We did a little bit experiments. We're trying to prune layers and measure their performance of a BERT model or some llama model. For BERT model is post-norm. For llama is pre-norm. You can see, I won't go too detail. So for example, here, this is a layer pruning performance of BERT, and on right hand is layer pruning of llama. So you can see a completely different trend. For BERT, the early layers, they suffer less. For llama, the deeper layers suffer, like they drop performance less. And also we train our own model to avoid any compounder effects. And we train our model with only differences post-norm here, pre-norm here. And you can see this significant difference, which shows if you train with pre-norm, your deeper layers always contribute less. Also, it depends. No, here is only difference in layer norm. So my hypothesis is deeper layers actually utilize or pre-norm actually cause deeper layers less effective because we know pre-norm helps train our model more stably. You can always stacking more layers if you train with the pre-norm. This is why pre-norm is dominating now. And post-norm, if you try it, it's very difficult to stabilize. And the reason here, we provide some theory. I'm not a theory guy, but this is very simple derivation. So if the reason here is if we use pre-norm, you can see the skip connection here. We don't normalize this path at all. So what's the disadvantage of this? If we don't constrain this line, we will have the continuously large variance, output variance of this deeper layers. As you can see, deeper as your model goes deep, the variance grows a lot. Why this is bad? So if we calculate the derivative of post-layer norm or pre-layer norm here, you can see there's one common thing, the Jacobi matrix of your layer norm. And if we can do a small assumption and we can have the Jacobi matrix, the derivative of Jacobi matrix of layer norm equals to this one. And the sigma x prime is actually your output variance. And because of the output variance of your deeper layer will becomes very large, which means this part goes this part goes to 0. And which means the entire Jacobi matrix of pre-norm this part will become 0 and it becomes identity mapping. Not exactly, but close to identity mapping, which means the deeper layers can just perform carrying your signal without adding too much informative signals. And this is also, this is our understanding why deeper layers becomes increasingly less important. And our fix is very simple. because we know the root cause is variance is too big, so we perform a scaling here. After each layer norm, we scale it down with the square root of depth. We do this just to avoid the hyperparameters. So it's a small, it's the current depth of the current layer. And it's, you can use these techniques, you can always deliver lower loss. And if you measure the performance drop of a layer, on the right hand is our method. You can see this is toy model, like a 100 million. The deeper layers can contribute more, but which means it's also it's more difficult to compress. And this is a layer-wise distance. So with our techniques, the layer-wise, the feature learned by different layers are more has larger distance. Yeah, this is all for my talk. Feel free to ask questions.